So we mentioned that with diffraction, we also get interference and superposition in bright and dark fringes. But how do we mathematically determine what those fringes are going to look like and where they're going to be located? Like we did in the last example with Young's double slit experiment. All right, well, let's take a look. Let's make a very similar circumstance. Okay, let's do the same kind of analysis that we just did, where we have, one beam leaving here, another beam leaving here, right? And, this here is the width of the slit, and we draw a line here, and we say to ourselves that this is going to be one full wavelength difference, okay? So you might be tempted to say, well, it's the same exact relationship as we had with the Young's double slit experiment, that we should just do d sine theta equals m lambda for all the bright fringes. But there's something very important that's different here. And that is that with the double slit experiment, you blocked all the light waves in between, right? But you're not blocking them anymore. We have to account for them. And now, let's, for example, look at a third wave that's right in the middle. That's at w over 2 over here, right? If that's at w over 2, then this difference here is going to be lambda over 2, or half a wavelength. Now, if two wavelengths are exactly half a wavelength out of sync, that's destructive interference, right? Let's say that I take a wavelength like this, right? And then I shift it over, right? So that it starts here now, right? And then obviously this continues back. That's shifting it half a wavelength, and now they're totally out of phase, and they cancel each other out, and you're left with a flat wave, right? So in other words, this beam here cancels out with this beam here. Now imagine I have another beam just a little bit below it, and then I pick another beam just below this middle one, right? That those two will be exactly out of sync, all right? And if I do another beam just below that and another beam just like that, those two will be off by half a wavelength and completely out of sync. So you can see that for every wavelength up here, there's a corresponding beam down here that actually cancels it out. So we're going to get the same relationship. So if this is theta right here, right, we're still going to get a sine theta equals, and remember, this could be any integral number of whole wavelengths, so I'm going to put an m there, right? Sine theta equals m lambda over the width of the slit, we'll call it w, right? So now we have this relationship w sine theta equals m lambda. And remember, this is just sine theta is opposite m lambda over hypotenuse, because it's a right triangle, w, okay? So this still is our relationship, but it doesn't give us bright fringes, right? We proved that because every beam up here cancels with a corresponding beam down here, this is going to give us dark fringes. So same relationship, but it gives us a different kind of fringe. Okay? So for Young's double slit experiment, we had the relationship, d sine theta equals m lambda, and that gave us bright fringes. For diffraction single slit problems, we have w sine theta equals m lambda for dark fringes. Okay? All right. This next slide here kind of reinforces that. And I just want to point out something interesting that happens in single slit diffraction problems in particular. In single slit diffraction, the central fringe is the most intense, okay, by a lot. And then the subsequent fringes that you see on the wall, so in other words, the central fringe is so intense, and then each subsequent fringe gets a little bit less intense until it dies out, right? And you don't see any bright fringes at all anymore, okay? And so it might be an interesting thought experiment to ask yourself, why would that be? Why would the central fringe be so bright and the others be subsequently less bright? Okay, but let us take a look at how we use this relationship to actually solve a classic single slit diffraction problem. So we have light that passes through a slit and shines on a flat screen that is located L equals 0.4 meters away. The wavelength of the light in a vacuum is 410 nanometers. The distance between the midpoint of the central bright fringe and the first dark fringe is y. So determine the width 2y of the central bright fringe when the width of the slit is w equals 5 times 10 to the minus 6 meters. Okay, so we basically want the width of the central bright fringe. How wide is that going to be? And remember, this could possibly have real-life correlations if we're, instead of shining light through a man-made slit, we're shining light through some kind of molecular, like biological structure. Okay? So let's suppose that we have a wall and we have a slit. Okay? And we know that there's going to be a nice big bright spot here, right? That's going to kind of, be the brightest right in the middle and then get less bright. Then there's going to be the first dark fringe here. So if we are looking for the width of the central bright fringe, we're really trying to find the distance here to m equals 1, the first dark fringe of this relationship. And we want to multiply it by 2 because we want the whole width of that, right? Because the central bright fringe lasts from the center all the way up to the first dark fringe, right? The central fringe ends where it turns dark, right? So in order to get the width of that, we want m equals 1, the first dark fringe. If we can find this y, right, where the first dark fringe happens, okay, then we can actually find this width of this fringe because we would just take 2y. Okay? But remember, y is equal to, well, I should probably just use the trig identity. So if this is theta, tan of theta equals opposite over adjacent. So that's y over L. We know what L is. L is 0.4 meters in this case. So I'll just write that in right here, 0.4 meters. Okay. And then we said that there's this kind of approximation where if theta is small, then tan theta is approximately sine theta. Okay? And so in this entire chapter, in this entire unit, you can always use this approximation. So this is the same thing as saying y over L equals sine theta. Right? But again, we know that sine theta is m lambda over w. So y over L equals m lambda over w. Okay? And there's a bunch of things we know. We know that m is just 1. Okay? We know that y equals, lambda is 410 nanometers, or 4 times 10 to the minus 9. Okay? We know that the width of the slits is 5 times 10 to the minus 6 meters. And this is also meters. Okay? And we know that L is 0.4 meters, which means that if we put this all in, I get the glorious answer of y equals about 0.032 meters or 3.2 centimeters. Okay? Now, are we done? No, we want the width of the whole central maximum. Okay? So to get that whole width, we want to take that y and multiply it by 2. So the actual width of the bright spot is going to be 3.2 times 2, or 6.4 centimeters. Okay? At least that's what I get. Go ahead and check it with yourself. Let me know if it works. Okay? All right. That is how we play with diffraction. It's a very, very similar relationship for single slit diffraction. The only thing is we're finding dark fringes instead of bright fringes.